Okay, welcome everybody. In the next couple of videos, we are going to look at different ways of representing solution sets to systems of linear equations. We'll take a look at homogeneous systems, non-homogeneous systems, look at the solution sets of these types of equations, and see how the solution sets might be related to each other. So in this first video, I just want to define what a homogeneous system is. So a system of equations is homogeneous if it can be written in the following form. So here we have the matrix equation. Matrix A times vector x is equal to the 0 vector over here. So this is a vector that comes out on the right side of that equation. So for example, let's consider the following system of three linear equations. x1 plus x2 plus x3 is equal to 7. x1 minus x2 plus 2x3 is equal to 7. 5x1 plus x2 plus x3 is equal to 11. So we can represent this system as a matrix equation where here is our matrix A. Here is the vector x. And on the right side, right, we don't have the 0 vector since the right side of this equation, we have 7 in the top equation, 7 in the second equation, and 11 for the third equation. So this is not a homogeneous system. However, if we modify it just slightly, so we still have x1 plus x2 plus x3 for the first equation, but now we have it equal to 0. And the second equation, x1 minus x2 plus 2x3 is now set equal to 0. 5x1 plus x2 plus x3 equals 0. This would be an example of a homogeneous system of equations because here we have our matrix A, here we have the vector x, and over here we have the 0 vector. So this indeed has the form ax is equal to 0. And so as we start to think about what solutions to these systems might look like, notice that if we're working with a homogeneous system, that a trivial solution, and by trivial solution we mean setting all of the variables equal to 0, this is always going to be a solution for any homogeneous system, because if we set all of the variables equal to 0, no matter what the coefficients are on the left side, we're going to have 0, 0, 0 equals 0, and 0 equals 0. So all of these systems, all of these homogeneous systems have at least one solution, which is a trivial solution. That is not the case for non-homogeneous systems. In fact, the trivial solution is definitely not going to work for a non-homogeneous system. So the question isn't how can we find one solution when it comes to homogeneous systems, but how can we determine whether other solutions exist, other non-trivial solutions exist? Okay, so how can we determine whether a system of linear equations in general, okay, even if we don't have a homogeneous system, so we have an equation ax is equal to b, whether b is 0 or something else, in general, recall that this system is going to have a unique solution if A has a pivot position in every row. So for example, if I had a matrix A which happened to have 4 rows, then we would require that each of these rows has a pivot position. So if this is the case, so if the matrix of coefficients, and now we're not looking at the augmented matrix, just the matrix A, if it has a pivot position in every row, then we just have a unique solution. And so if we had a homogeneous system like ax is equal to 0, and we're in this first case where we have a pivot in every row, then there would be a unique solution, and that solution, again, would have to be the trivial solution. So if we had in R3, that would mean the only solution would be that x is equal to the 0 vector. Okay, on the other hand, if we're working with this equation ax is equal to b, then that equation is going to have an infinite number of solutions if the matrix A has one or more free variables. So what would that look like? For example, if matrix A, after we do some row operations, we put it into its reduced row echelon form, if it looks something like 1, 0, 2, 0 in the top row, 0, 1, minus 3, 0 in the second row, 0, 0, 0, 1 in the last row, well, then we can see that this third column does not have a pivot in it. So in fact, the variable x3 must be free. And that would tell us, therefore, that we have an infinite number of solutions. So the size of these matrices, I'm just making them arbitrary. So in this case, for example, we would be working with a system of 3 equations and 4 unknowns. And that's why we have a 3x4 matrix. But this is true no matter what the size of matrix A is. And it's important to note that here A is denoting the coefficient matrix. So we are not including a column for B for the augmented matrix. So these 2 bullets are true no matter what the vector B is over here, whether we have a homogeneous or a non-homogeneous system. But if we are just considering what would happen with homogeneous systems, well, if the equation AX equals 0 vector, this is going to have a non-trivial solution if and only if the solution set has at least one free variable, because if there is a unique solution, then that solution is going to have to be the 0 vector. So in order to have non-trivial solutions, this means we need to have an infinite number of solutions beyond just the 0 vector. And this means that the matrix of coefficients should have at least one free variable once we put it into reduced row echelon form.